Joe has just arrived. Hello, Joe. Welcome to our meeting.
Great to be here.
Thank you for joining us today for our 25th anniversary celebration. It's a pleasure to host you here, even online, virtually. I'd like to introduce you to our audience. I have a couple of words to say about you. Professor Paradiso is the Associate Academic Head Program in Media Arts and Sciences in Massachusetts Institute of Technology. He directs the Responsive Environments Group, which explores how sensor networks augment and mediate human experience, interaction, and perception. After 2 years developing precision drift chambers at the Lab for High Energy Physics in ETH in Zurich, he joined the Draper Laboratory, where his research encompassed spacecraft control systems, image processing algorithms, underwater sonar, and precision alignment sensors for large high-energy physics detectors. He joined the Media Lab in 1994, where his current research interests include wireless sensing systems, wearable and body sensor networks, sensor systems for built and natural environments, energy harvesting and power management for embedded sensors, ubiquitous and pervasive computing, and the Internet of Things, human-computer interfaces, space-based systems, and interactive music and media. He has written over 350 publications and frequently lectures in these areas. In his spare time, he enjoys designing and building electronic music synthesizers, composing electronic soundscapes, and seeking out edgy and unusual music while traveling the world. After receiving a Bachelor of Science in Electrical Engineering and Physics, summa cum laude from Tufts University, while working on precision inertial guidance systems at Draper Lab, Paradiso became a KT Campton Fellow at the Lab for Nuclear Science at Massachusetts Institute of Technology, receiving his PhD in physics there for research conducted with Professor SCC, Tang's group in CERN in Geneva. Thank you again for being here, Joe. It's very nice of you. It's very kind of you to join us in this special event. I would like to announce the title of your talk, Examples of How Artificial Intelligence, Shared Environments, and Distributed Sensing Are Changing Interaction. Thank you.
Thank you very much.
And I'll pass you. The screen is yours. Thank you.
Okay. Thanks a lot. It's great to be virtually back in Turkey. Speaking about music, I remember when I was in Istanbul some years ago, I took the ferry across the strait and found this wonderful place for psychedelic Turkish music. It was just such a fantastic introduction. Can you guys hear me, or am I locked up? I'm not sure.
Yes,
Hello?
we can hear you.
Okay, good, because you were frozen.
Not everybody can say that.
I'm coming across. That's good. So
I know that you prefer to be interactive, but
we all do.
Sorry to interrupt you. I know you prefer to be interactive, but this is set up like this. So.
It's fine with me. It's just I wasn't sure the screen was frozen. It looks good, so I'm going to assume it's not. Let me know in the chat or whatever if it locks up. So I'm going to share my screen here, I don't want to install the Zoom audio device, so I will say no. Hopefully this works. So I'm going to go very quickly through a bunch of projects in my group that talk about not so much exactly AI, but we leverage AI now quite a bit. AI is a tool that all of us are using more and more. I do a lot of work with sensor data in my group, and it's very much not just about how I get the data and how I make the sensors, but really how the data is interpreted in different ways. And we've long used many tools to do that, processing in the network of sensors itself, also processing the back end. And it's intriguing to think about how AI plays a role at all levels. And I'll allude a little bit to that, but I'm going to more give you examples of the kinds of things that we do. So it'll be kind of an application-focused talk, very, very fast. So we work at different scales. I don't have time to give you justice to most of this, but we've done work at wearables, the Media Lab, for a long, long time, many, many years. And my group is one of the early groups doing wearable sensing at the lab. We still do it. I'll hopefully talk about these glasses in a moment, for example. We do work at building scale, sensors in buildings to make the building run more efficiently and different ways of representing that data. Going to be a crucial part, I think, of saving energy as we move forward. Sensors in landscapes as well, outdoor sensing to see how landscapes are changing, but also to connect that data to people in different ways. We use virtual worlds a lot for that. And now more and more, we have projects in space. Our new director at the Media Lab actually came from a space background, human space flight. But I did it myself as well. When I worked with Draper Lab for years, I was in the NASA group doing a lot of work in spacecraft control. So now we're looking at a few projects in space, but mainly looking at sensors, sensing material, even sensor networks in space now. Different era for space. As you heard, and as I mentioned, I love music, lots of different music. This is one of my favorite things to do in normal life, and let's go to a concert. I'm sure many of us have the same passion. You have such great music in Turkey. I'm sure you're going out to shows as much as you can in normal times, but we don't do it very much. This is a show I saw at the Roundhouse in London. I was giving a talk at Imperial College some 4 or 5 years ago, and it's a wonderful theater. You're just packed with people. It's exciting to see what the band do, but you also react to the fact that there's a crowd there. So it made me think a lot about what's special about being somewhere. What's special about presence. This has been a theme in the group for a long time, and every time I go to an event like this, and when I think back on it now, it really comes into the foreground. What's special about presence? This is what we have now. I was at a festival, virtual festivals of band in France. They were great. I watched in my living room. I have my pet rabbit there. It's very comfortable. I have a great sound system, but it's not the same as being in one of these real festivals. This is what we got now. It's one of my early group meetings in the pandemic. Great to have so many wonderful people. We're all trying to figure it out. You can see no one's entirely happy there. It's not the same, right? This is not the same as being in front of you guys, seeing your reaction. But we do what we can. We make do. I think there's lots of room for improvement. And it gets to the question of what is it about being somewhere? Now that we have sensors all over the place, can we start to expand experience by connecting to the sensors in different ways, utilizing all these new interactive techniques that are emerging? And my group has been looking at this now for, a good part of the last 15 years. This is an article we wrote in Scientific American. It appeared in many other countries as the cover article, as well as the US. You may have seen it in Turkey. And it was all about, even back in 2014, how people will connect to the sensors that are all over their environment, and how you naturally will try to expand perception in different ways. So this is one of the first examples we did. It's the Media Lab, our new beautiful building. If you could look into it, you'd see maybe all these sensors, right? So this is a visualization of sensors from the HVAC, which are these little fires that are red and white, the temperature, humidity in the atrium, people moving around, which are these arrows and areas. Also, if something is too hot or too cold, we have a blue or a red ball around the temperature sensor. So you rapidly see a lot of what's happening in a space through an animation. It's now called digital twin. Back then there was no name. We called it cross reality. This is 2012. We'd already been doing it for a little bit. So here we're zooming through the building. You're seeing the sensors that are out of spec. You're seeing the temperature, humidity in the atrium, experiencing in a new way. And we have audio. We have microphones all over. My group tends to be very skilled with audio. And as you move around, you can hear the sounds from microphones if you're near in the virtual world, near where the physical microphone is. So here I'm going near a microphone. You can hear people moving around, and you can hear people talking. You hear in a moment, but we're very careful about that. We don't want to spy. So at the sensor node, we drop packets of audio. So this is somebody speaking English, but you can't understand anything. You can't even reconstruct it properly. But you can tell if they're laughing. You get some idea of the affect there, the presence, the feeling of presence. That's with RFID. People move around. You can see their icon appear, so on and so forth. Then we move to an outdoor space. Outdoor spaces are real rich environments, as we know. We miss them when we're not connected to them. So we had a Cranberry Bog in Plymouth that is co-owned by one of my colleagues, retired faculty at the Media Lab. And she was fascinated with the idea of trying to collaborate with us and put sensors all over to capture this whole process of the Cranberry Bog being turned into a wetland. She was restoring it to its natural state. It was a massive site. I think it was on the order of 20 acres. And we captured the transformation. This is after it had been transformed within a couple of years. And in the process, we put microphones all over the place as well to capture the sounds of the wildlife, and we can stream it to people so they can hear these sounds. It's wonderful to hear, birds and frogs and things like that. Hear a change over the course of the year. We even put in cameras to show it. This is not so unusual, but we also built a framework to recognize the different kinds of species. Again, using deep learning and AI, we trained it on stock sounds of different birds. For example, here we could separate different classes. This is done by a visiting student from France. We've got French colleagues now that are taking this much further with us. We did it in real time. So as the microphones produce sound, you could see an icon come up in the virtual world as to what was going on there, be it a different kind of a bird, be it a plane flying over, or some other sound, some insect, frog, so on and so forth. And during the day, of course, you can see this classifier working. If you look at the cache data, you see the frogs in the evening pretty much. This is during the spring. And then you see the birds come out in the morning and later in the day. And then other sounds during the middle of the day when nature's a little quieter. And then if you drill down, you can see the species of bird just starts to break that apart. So we can start doing these things with sensors in natural environments, really getting a feeling for the pulse of the landscape, the pulse of the environment, how different kinds of species are coming in and out, in this case, through the acoustic signature. We've got lots of other projects to localize them. There's no time to talk about that. And to reproduce them in virtual worlds as well, where you can reconstruct the sound and drop it in wherever you want. We have sensors we built, very low power. We built a sensor net of 100 to 200 sensors that were deployed there, still are there running. They run almost all day with a solar cell. They measure lots of different parameters, and they can be extended. Since it's a reformed wetland, it's a wetland now, we put sensors in to measure soil parameters. So all of them have that extension, but we can put lots of other sensors in to talk to them with an app to configure them. This is some of them in a transect. This is a line of sensors going down the area. They form their local network, and then they talk to Wi-Fi base stations that talk with a directional antenna, high gain antenna, to a front end that goes to the network. So we cover this massive property with an architecture like that. And of course, we can tunnel the data into virtual worlds. We do some science with it, see what happens to the wetland over time, but we can also bring it up to people that can't get there. Of course, walking through a wetland, it's very difficult. You have to have boots. There are ticks that can bite you and give you disease. So in the virtual world, you can visit that free of any of that. So we tried to make virtual worlds vivid, where we took the landscape, modeled the same landscape in the virtual environment, but tunneled the sensor data in through creative animation of different sorts. And this is a video. It's a few years old now, but it shows the weather mirroring the weather in the real world. So we call it an avatar landscape. The music comes from the sensor data. So if it's hotter, colder, humid, less humid, the music will change, and it's localized. As you move around, you hear different sounds, different visualizations to accentuate the sensor data, for example. And it's in a game engine, so you can move through animals. The virtual animals will feed on the sensor data, and they will change their appearance depending on whether it's been hot or cold or humid or whatever. Another mapping, audio and visuals. Again, we've invited composers to do pieces on top of the data, so we have many different interpretations. I believe that sensor data is going to be the canvas of future artists. They're the ones that are going to bring it up to our eyes and ears. We built vehicles so you can browse the whole area with a vehicle. This is Don Haddad's work. Extremely interesting, where you can have no motion sickness because you're in a vehicle, and you can have access to data as well as the visualization. You can play in both. And that leads to thinking about the future of control panels. And we've been thinking a lot about this, these control environments, mission control spaces. If you look at the evolution of spacecraft and cockpits, the early days of Apollo, it followed aviation. This looks like a really big pilot's control surface, like you would see in a plane at that time. Of course, more exotic, it's a spacecraft. Days of shuttle looked a little bit like the aircraft at that time, where you had video displays and things like that for some of the instruments. Uh, Again, a bit more exotic because it is a spacecraft. But now the SpaceX Dragon capsule looks like my Tesla. You've got a touchscreen interface. So it's changed with the times, changed enormously, and really begs the question, how we're going to be interfacing with in these vehicles, in these environments in general, with space operations, with operations even in factories and other places, as the affordances update and as the whole idea of presence changes. So this is from one of the Matrix movies. It's a fantasy of people in a virtual world with direct neural connection, where this is what they see in their brain, but in the real world, they're kind of passed out in an ugly environment. A few people are still on screens in the back. But yeah, this is kind of what we'd aim for. I don't know if it would look exactly like this. This is still looking like a GUI. It could be very different. But what is this immersive world going to be when we can bring this data really up to people? So my student Don Haddad has been looking at lunar operations together with people in the Air Astro department at MIT. We're actually putting a sensor payload, I think, on the moon in a rover like this. But can you take all the data coming off of things like this, bring it up to people in different ways, aid in mission planning through immersive VR kinds of operations? So here he has a rover going through the VR environment. It's the simulated landscape of where the rover is going to be moving. You can look at sensor footprints, look at real-time data dropped in different ways. You can zoom in and out. You can have people at different locations have different kinds of access to it, which is one of the really interesting things we're doing. So this is the just one piece of a very big project, but I think it's intriguing to think about how people will cooperate using virtual environments as the intermediary in complicated operations. And then what if you're physically in a place like this? So this is my student Gershon at the Tidmarsh site, the wetland where we had all the sensors and the microphones. But he's got an apparatus in his head where he can basically have all the sensor information tunneled into his real-time hearing in this case. And it responds to how he's moving his head and responds to whether he's being attentive or not. The early version had lots of senses for attention. In addition to bone conduction, we didn't want to cover the ears. This is an extra sense of hearing. The later version was much simpler. We for attention, we could just look at how still your head was. That was very effective at gauging at least how focused you were. You know, you could walk through this landscape. We track you. We'd see where you were, and we could have the sounds appear as if you had an extra set of ears. So this is a guy from Bose that worked with us. He's one of their fellows, designed all of their great headphones. And for him, this is a very different kind of experience. This is a naturalist we work with. So she's talking about, if you can hear it, all the way it responds to how you move your head. It is like you have an extra set of ears. I've tried it, and it's just an amazing experience. We do a lot of work now in what we call cognitive audio, blending AI and microphones directly, where you train your audio system to hear the way people do. Now we have microphones all over our environments. They respond to their names. I'm not going to say any of their names because if I do, they may wake up on my watch or something and start to interrupt. But that's a very simple way of doing things. What if you can train these systems to notice things like people do? We talk about even for applications like in cars, where what sounds do you bring into the actual cockpit of the car? There's sounds that would be important to people. So you can do it spectrally like people have done, but it's very coarse. It isn't the best way to do it. If you train a deep learning network to listen like people do, it will respond with sounds that are more valent or relevant for people in different ways. And Ashwarya has been developing a whole system to do that. That's essentially what she's saying here. You know, what kind of sounds do you remember? She has done a system where she took a whole day or a whole week of somebody's life and would compress it in different ways. So, and you can, again, you can bring it back to you with different emphases depending on how the network has been trained. In this case, there are two of them. There's one network that's kind of looking more for music or things that are musical. There's another network that's looking more for speech. And this is about a year ago. If you listen to This Day of My Life, if you can hear it. Again, lots of music. I was listening to a lot of Indian ragas at that time, so you hear a lot of things like that. That's me playing my keyboards and synthesizers. So you just have all these kind of musical sounds. This is one that's emphasizing more speech. And it's some microphone artifact.
Sure. So I don't like it. There's just no music on her phone. Oh, there might be. No, I went there. Small enough area to make it into one experiment. Switch. You got to switch. I didn't see any of that because look.
Well, there you go. Again, you can begin to compress your day in different ways. Things that are important to you, things you would remember, you'd notice, things that could be more musical. You can turn the network in different ways. So she's doing her PhD thesis in about a month, and she's got lots of great results. This is only part of what she's doing. The whole idea of cognitive audio goes very deep. We also are looking at measuring other things on people with wearables. For instance, attention is one of the real last frontiers of user interface. It's difficult to really measure. We have some shortcuts to it, like we did at Tidmarsh. An environment like that, if you're headed still, you have some idea that you're paying attention. In general, you want to look at other factors. You can look at how the eye's moving, ideally look at pupil diameter. You can look also for cognitive load, which is another relevant thing. About temperature difference between the nose and the temples. You start looking at the EEGs. People have done lots of bits of this. We built a set of normal glasses that measures many of these parameters and then fuses them to build a model of attention. And then using it to build different kinds of user interfaces that ideally help to conserve your attention. One of the problems in our life now is our attention is so fragmented. It's hard for me to remember what I was supposed to do because I'm jerked into something every minute. Is there a way to streamline your life to have your devices start to act to conserve attention in different ways? So we have built a system to do it. It has thermopiles and sensors and IMUs and senses the eye doing different things. We built it actually like a set of glasses. It's quite nice. Doesn't look so unusual. That's more about how we built it. The students learned a lot about how to build these things, working with glasses manufacturers at the Media Lab too. We have many industrial partners. And we have data from it now. It's hard to get user studies during quarantine, but we have some. And sensors are all working, and we're seeing some indication of cognitive load. I mean, it still needs more integration to really do it better, but it looks very promising. So we're ready to start doing more testing in the wild with this now. We're going to roll it out. We got about 10 of them. And yeah, lots of applications. Learning everywhere. Talking about learning online is kind of what we're doing now. In the future, we're going to be learning under the Internet of Things, where we can always be exposed to information. If we're driving a car, if we're sitting around, the system can decide that, okay, this is time maybe to prompt you in a way or to give you information because you're more receptive to it. It's going to be a partnership with learning pretty much all the time, everywhere you are, in a system that's responsive to your mental state. So that's a whole different way to think about it. And we're intrigued by using interfaces like this to look at. Of course, the students want to do events and things like that with it too. We're the Media Lab. I don't know if I have any time. Should I keep on going quick or should I stop?
I think you can still keep on a couple of minutes. Don't worry,
Okay,
no problem.
good. So
Because it's very interesting. So I'm sure so many people are also following in the same interest.
I think I can go very fast now, and I'll just go a few minutes to get through it. We've thought a lot for years in my group too about what we call sensate media, where you combine sensors and materials and processing kind of in a soup. So it's making a sensor network like we used to make in large scale environments like we did Tidmarsh, you do in buildings. You're building a sensor network now on a substrate. It could be a fabric, could be flexible electronic skin. We've had many different versions of it over the years. This is some examples of dense sensor networks that approach the whole idea of sensate media that we've done. A cork board with sensor nodes that talk to each other through IR to study routing and information processing in sensor nets. A skin that covers a ball, basically. Each one is a sensor node. Floor, this is a flexible one. This is a piece of tape with the sensors all along the tape. So it's like looking at sensors as commodity in material. Many different versions of them that we've made. And we've done lots of work in electronic fabric in the Media Labs, starting in the 90s, one of the first places to really build systems that worked using electronic textiles. And my student Ermindy has brought it back into my group in the last years, making electronic fabric too. So, he's looking at stretchable connections. He's also worked with Genentech, a variant at the lab, looking at processors like what we did in the past with sensors, but embedded in with stretchy interconnects and doing it in something like a fabric substrate. He's done many versions of this. He's looked also at sensate weaves, where you can actually weave fabric in a certain way to sense different parameters. He's made large-scale fabrics, things you can wear, things you put on the floor. He's even made keyboards, which of course I love, that can sense different things. They're electrochromic, so they can change color too. This is me. I can actually play it. This is his earlier version. So it's one of the first things that we built. That's a musical instrument you can be a little virtuosic on. He's got an even better version of it now. Measures many, many different parameters. Changes color. You can see it start to do that now. And lots of garments. So you can basically measure, the distribution of pressure and stress and strain at different parts of your body. And he's got lots of applications for that, from astronauts on to public health. And he does machine learning on the data too, to really figure out your gait, how you're moving, if you're doing something wrong, if something is wrong with your physiology somewhere. He's integrating that as well. Lots of stuff from Remedy. He's got beautiful work. I'm almost done here. We also are putting this in space. So we're putting sensate threads into fabric. They're already lining spacecraft. It's something they call beta cloth spacesuits, and the white fabric covering spacecraft. That's a special, almost like a Kevlar cloth that's made to withstand space environments, and it's a thermal coating as well to even out the thermal distribution. We're looking at integrating sensors into that to make it sensate, like a real skin. So you can sense micrometeorite impacts, for example, or sense damage to the spacecraft. So my student Juliana has been putting in piezoelectric fibers, and we have launched this on the space station. It's running up there now, a passive sample. It's working there. She's actually shooting microparticles at it in a lab, but now it's running up on the ISS. So there's a sample that's been there now for about a year. This is before she launched it on the left. At the right, this is after 8-9 months on the space station. We see some artifacts. We want to see how the material shows up. This is a passive sample. We think that this little yellowed area in the middle is where someone touched it with skin oils. And in space, atomic oxygen and temperature extreme stuff happens. We'll be getting it back in some months to analyze. But in the meantime, she's launching an active sample in February to actually in real time track micrometeorite impacts and see how the actual electronic properties of the fabric age over time. Many different kinds of sensate fibers in there. So we're looking at different approaches. And of course, we have other projects. This is Feng Zhang's micro robots to look at space structures, to look at their health. We've then run them in zero gravity flights. We have zero gravity flights every year at the Media Lab. So here are the robots basically just doing their thing in zero gravity, moving around. And again, they can measure lots of things about the structure. They're rolling across in addition to take images to look for damage, so on and so forth. And finally, my student Feng Zhang is looking at, as I mentioned, lunar sensor nodes. So based on the experience we have at Titmarsh and thinking about what we want to do in a harsh environment, physically putting a sensor node out on the moon to measure different parameters. And we're talking to a company that makes a rover. I think we may have a manifest to put these on a rover so we can send them out. We look at ballistically deploying them, where ideally we'd shoot them out. You can aim like a gun and shoot this thing out with a spring, because the rover can't get everywhere. You can just throw a sensor node over to where you can't get and make a measurement. You can't use a drone on the moon. There's no atmosphere, but you can shoot things pretty far. It's once there's gravity, you know exactly where they land. So we're developing the node. We already have a node developed. We have a chance to fly it actually, if we can finalize by next spring. This could fly within a year to the moon. It's this node. You can change sensors, reconfigure. It's like a microsat based on that idea. And that's us finally. So thank you very much. This is a good part of the group. We can start to be in person again in the US. And yeah, thank you very much.
Thank you very much. That was an excellent talk, very condensed. And thank you for touching all the different types of things you're doing in the Media Lab. I'm really excited to watch it. The visualization of sensor data on music and art, and I think that those will drive music and art in the future as well. all these spacecraft interfaces. I have some notes, but I could actually ask many questions, but one of the audiences asked, maybe I should start with that. The last textiles you have shown, do you think these will do some measurements on EEG, GSR? I think it's our medical informatics student. He's asking, these textiles you have shown us, can they actually measure EEG or GSR? Can they do those sort of measurements, or do you have any plans for those sort of studies? He says.
Yeah, absolutely. Ermindy, I believe, has measured GSR on them. EEG, people have made textiles that can do EEG, so you can do that as well. He's doing mainly EKG, right? So he has a chest garment where he can do EKG, so that he does. And if you do that, you can do different things of that sort. They also measure stress, so you can get breathing. I mean, there's been a lot of work in Europe over many years of vests to measure all of this, but at this point now you can knit them much more elegantly. They can hold up much better. And he looks at even blood pressure now, because he sees how different parts, so you can constrict it and start to see maybe a pulse response or a different kinds of differential response to blood flow in different parts of the body. So it's one of his parasaltic suit he's making now is looking at that. So there's a huge frontier, both as an electrode, which is what you mentioned. You can just have the conductive materials in there, but also measuring strain, stress. You can get into other physiological factors that way too.
Thank you. So I haven't read many questions so far, but thank you very much. It was a very interesting speech. Thank you so much. Seeing all the research you've been doing.
Thank you too.
Currently doing.
It's a pleasure to virtually visit you guys.
Thank you. We hope we could do it face to face sometime for maybe 30th anniversary celebrations. We could do it face to face and hope to meet you here in person or before then. Thank you for joining us today.
My pleasure.
And sharing your time with us. Thank you.
Thank you. Have a good event. Bye-bye.
That's Paradiso. Bye. Thank you.
Thank you, Professor Özkan.
Okay, we'd like to thank
for joining us today. Thank you.
Okay, Kiraz.
The Graduate School of Informatics provides a unique research and learning environment in the interdisciplinary fields of information and information technology. Our faculty and students are a diverse group with a wide variety of experiences and interests. In the next session, I invite the department chairs to introduce our graduate programs and the active research groups and labs in the Informatics Institute.